I'm Joshua Dalby. I work for a company called Ricardo. I'm the global head of research and development at Ricardo. I'm going to talk to you this morning about greenhouse gas removal through combining biochar production and carbon capture. So just a brief intro to Ricardo. In case you're not aware of us, we're a global strategic environmental and engineering consulting company. We've actually been around for 110 years, innovating in the transport and energy sector for a long time. We're present in 23 countries, about 3,000 people globally, and at any one time we have about 2,500 live projects. So we're active in lots of different areas, as you might imagine, but I won't really touch on a lot of those areas this morning. One of the areas we operate in is in the biomass and waste sector. So we've got a lot of technology experts that do consulting work around anaerobic digestion, waste to energy, waste to fuels, biomass, gasification, pyrolysis, etc. So we'll do a lot of technical due diligence for projects. We'll advise national governments on policy and strategy going forwards, and various other things. But we're also an engineering company that develop our own solutions and technologies, and so we use some of that expertise and our engineering know-how to install a pyrolysis CHP demonstrator plant at one of our facilities, and we've spent some of the last couple of years or so trialling different feedstocks, producing biochar from them and understanding how that system responds. So I'm going to slightly contradict what you said before, but not massively. So pyrolysis-based CHP systems, I would say typically capture around 50% of the carbon in the feedstock as biochar. Obviously, it can be less, and depends on your pyrolysis conditions. So it obviously is an effective way. That's probably why most of you are here. Effective way of carbon removal. Heat's often required to sustain the process, and so that's often generated through combustion of the syngas, which comes from the process. And then obviously the excess heat from that combustion can be used for generation of electricity or biomass drying or heat export. The syngas primarily consists of hydrogen and CO. Some CO2 sometimes comes off. Again, depends a little bit on the architecture of the pyrolysis system, and some hydrocarbons as well, CH4, but also other hydrocarbons. And when that's combusted, when the syngas is combusted in the presence of air, then the flue gas composition is typically around 10 to 12% CO2. So there's still some CO2 there. So 50% of the carbon's captured, which is great, but there's still about half of it in the feedstock, which goes into the flue gas. Because we're comparing carbon versus CO2, what that means is for a plant that produces 2 kilotons per annum of biochar, that would equate to about 6.7 kilotons per annum of CO2 that's available in the flue gas. So what do you do with it? Well, you could capture it and sequester it. I've put a map up here of the existing and proposed infrastructure in North America. So there's some pipelines already operating, particularly down in the south. There's quite a few proposed up in the north, including some in this state and the surrounding states. So you could sequester that. That would lead to additional revenues from the carbon credits. But obviously there's a transportation challenge, so realistically your site would probably need to be located pretty close to one of those pipelines, and for it to be viable. And then also, a lot of this infrastructure is designed for very large scale power plants, and there might be kind of barriers to access the infrastructure based on kind of minimum injection amounts. So it's feasible, it's possible, but not necessarily straightforward. So then the other option is then producing food-grade CO2 from the flue gas, which obviously then isn't sequestering it, but opens up opportunities for it to be utilised. The price of food-grade CO2 in the US has increased rapidly in recent years. It's also very volatile as well. You can see a kind of big spike around 2008, but then also in recent times, triggered by the Ukraine war, then there's been a significant spike there. The reason behind that is because food-grade CO2 often is produced from fertilizer production, which is inherently linked to the gas price. So you get a spike in gas price, or you get a disruption in terms of gas supply because of trade relationships. You get an increase in fertilizer price, you get an increase in food-grade CO2 price. And actually in the US, you can see it's particularly high price compared to other countries here. So it's it's a premium product. It was much more commoditized back in the kind of 80s and 90s, but there's obviously a limitation in terms of the demand, in terms of supply to meet the demand that there is. So that high kind of market price in the US could be quite a game changer for annual revenues. Now, obviously, there's a lot of assumptions here, and I'm sure it won't match exactly your plant if you have a plant, but I've just produced some indicative values here for a plant that processes around 10 kilotons per annum of biomass. So obviously you've got the kind of cost of the biomass, which will vary obviously depending on where you're sourcing it from. You've got the O&M. You might generate some electricity, but the price or the value of that in the US is pretty low, so you don't really benefit too much. You might have some excess heat. You will certainly sell your biochar and the carbon credits related to that, and obviously you aim to get the best price you can there. But using these kind of indicative numbers, which are based on kind of public domain information, it's marginal, the business case, just about makes money in the end, but it's fragile, depends on stable low cost biomass price and stable high cost or high price of biochar and carbon credits. And I think that reflects a lot of the conversations that we've heard in the conference anyway. So, but actually then if you look at the CO2 revenue based on that market price and the amount that's in the flue gas, it's incredibly large in comparison. So there's definitely huge potential there to change the overall business model for a pyrolysis plant. Okay, the formatting here isn't quite right, but don't worry, you're just missing the footer of the slide. So how can you do it? If you were interested in doing this, what are the options? There's lots of people developing CO2 capture systems. We've kind of classified them in these 4 different spaces. So the first one is solvent absorption, so a liquid that flows around a system. Typically it's a temperature swing absorption process, so at low temperature the solvent will absorb CO2 and at high temperature it will release it, and you keep recirculating this solvent around. That's pretty proven. It's in place in a lot of large coal and gas power plants and being kind of widely adopted across that large energy sector. It's pretty suitable for quite low concentrations of CO2 in the flue gas, so it can work with high concentrations but also works pretty well with low. Disadvantages of solvent absorption are the energy that you require for solvent regeneration is quite high. It's a thermal process, so you need to heat all of that solvent up to release the CO2 and then cool it all down again to absorb it, so energy intense. And also the solvent degrades over time depending on the conditions, so that can impact the operating cost. The second kind of category is sorbent adsorption, so this is where you have kind of almost like ceramic kind of particles or beads, and rather than the CO2 being absorbed into the material, it adheres to the outside, and so you operate that it kind of swings between high and low pressure environments, so it adsorbs the CO2 at high pressure, and then when your beads have adhered as much as they can, you drop the pressure and it releases it. So that's it's a good option. Lower regeneration energy required than solvent absorption typically, but it needs quite high operating pressure, which adds some complexity in the design. At the moment, that's quite expensive technology, and those ceramic beads that I was talking about, there's concerns around if they can really last the lifetime that we would expect, so they would eventually lose some of their material, and then you'd have to replace them. So some disadvantages there. The third one is membranes. So these are fairly common in anaerobic digestion plants that separate out their CO2 to produce biomethane. They're pretty small footprint, quite commercially available already. But to produce CO2, pure food grade CO2, they're not necessarily the best option. The downsides are they need very high operating pressure. So they're basically, you force the mix of gas through these membranes which separate out. So some of the species pass through and some are retained. So it needs quite a lot of high operating pressure for that, which then leads to a high electricity demand. Fairly expensive still for what they do. To reach food grade CO2 purity, you need multiple units. It's easier if you're just using it to produce biomethane, but you end up with the CO2 which has got other things in it as well, so then you have to have additional membranes. And there's also concerns around durability as well of the membranes. And then the final one on the slide here is physical separation, so cryogenic process. Doesn't need any regeneration, so you don't have to swing between high temperature and low pressure or whatever. The CO2 is captured in the solid phase as dry ice, which is nice and compact, but it's still relatively early on the technology readiness scale at the moment, still really in research. No one's particularly deployed it at scale, and obviously you need fairly high electricity requirement to chill that flue gas down, because the concentration of it is not so high. You've got to chill everything else in there as well, including all the nitrogen. So really, best solution, in our opinion at least, is solvent absorption, because despite the requirement for energy, it's a heat-driven process, and a pyrolysis system with syngas combustion has heat available at the right kind of temperatures to help here. So that's the system that we've used and developed, the Biochar technology. We have an integrated CO2 capture system onto a pyrolysis CHP plant, so that demonstrator plant that I showed you earlier. You didn't see, you'll see in the coming slides images of the CO2 capture system there. So how it works is we have the biomass coming in the bottom left of this chart here. So pyrolysis and then syngas combustion happens within that unit. We take the biochar out from there. The flue gas passes through into a heat recovery system. This particular one is a hot air turbine so it uses air as its kind of cooling medium, and that gives us our heat and electricity export. The flue gas passes through and goes into the CO2 absorption column, where the solvent then comes in lean, so without any CO2 dissolved into it, and leaves rich with CO2 absorbed. The solvent goes across to the stripping column, which is at higher temperature, and the waste heat from the hot air turbine is high enough temperature for us to be able to drive that stripping column. And the stripping column then, or the solvent then, you need to cool down again so that you can absorb it, and so we also use that heat that's rejected at a lower temperature and use that for drying our biomass. So it's a very kind of integrated system where we're using the available heat at different temperatures and then reusing it for different uses. So we have an overall potential for very high carbon capture here, and we also have the four valuable outputs in terms of heat, biochar, electricity, and then the CO2. That system or that process is now patented in the UK, patent that we filed, and the US patent is pending as well at the moment. I think this is my last slide. Yeah. So pros and cons. capturing CO2 from pyrolysis flue gas specifically. So that process fundamentally will work on the back of any flue gas, whether it's from a gas engine or from a biomass plant. But specifically, if we're thinking about it from a pyrolysis system, the nice thing, as I mentioned before, is that high levels of thermal integration mean that the waste heat after our electricity generation is sufficient to drive that CO2 capture system. So we're not having to add anything in addition to the plant. And the heat that we reject, which is the majority of what goes across to the system, is then recovered at a lower temperature and is used for biomass drying. The other advantage is that the low oxygen content in the flue gas actually reduces the oxidization rate of the solvent. So I mentioned that one of the drawbacks of these systems in general is the solvent degradation over time, leading to a replacement interval. But that's hindered by oxygen in the flue gas. So if you have a system like this on the back of a gas engine that's running very lean, they'll have a high amount of oxygen in there that will degrade the solvent. In a pyrolysis plant, that's not the case. So we have relatively low oxygen concentration, which helps in terms of replacement interval. And then I mentioned also CO2 capture from anaerobic digestion, which is well established. Certainly in the UK, there's a fair number of companies doing that. One of the challenges with anaerobic digestion in capturing CO2 from it is the variability, because it's a biological process. You get changes in the feedstock and it changes what's coming out, and then the CO2 purification is challenging. One of the benefits here from syngas combustion is that even if you have some levels of feedstock variability and contamination, the syngas combustion process removes some of that from what's in the flue gas, and means it's a bit more reliable in terms of outputting a certain purity. Some of the challenges are that we've got relatively low combustion temperatures, certainly compared to gas engines. The pyrolysis plants run fairly cold. I know it's still hot, but in relative terms, it's cold. That means there's quite high particulates in the flue gas, and so we need an upstream scrubber to remove those particulates, because the CO2 system, there's some very fine tolerances in the absorber and the stripper columns, so you don't want those kind of gaps to be blocked up with the particulates. Then if you have a scrubber, in this case we have a wet scrubber here, you obviously introduce water into the flue gas, and then that results in difficulty just in terms of dilution of the solvent. So solvent is water-based, and obviously you're cooling down the flue gas to go into your absorber, so then some of the water comes out. So that can, if you don't get the balance right, that can mean that you need to keep topping up the solvent to make sure you've got the right concentration, and then you've got to purge it because you've got too much volume in the system. So that's just some of the challenges that need optimization and work. And then I mentioned in terms of anaerobic digestion variability on the CO2 quality, while capturing CO2 on a pyrolysis plant is still better than an AD in terms of variability, there are still some feedstocks that will produce contaminants in the flue gas that will pass through to the CO2. So if you want to produce food-grade CO2, you've got to have a really tight tolerance around a number of different species. And so you need to be a bit careful on some of the feedstocks. But the testing we've done so far, we're pretty confident on a lot of woody waste streams that we can hit food-grade standard. So I think that's me done. Yeah, so any questions? I don't know how much time we have for questions. Probably all right.
You've got like 24 minutes. Yeah.
Great. Cool.
Hey, you said that most food-grade CO2 comes from ammonia and like fertilizer production. Obviously, power plants, like fossil fuel power plants, produce more CO2. Yeah. So what's the barrier to power plants making food-grade CO2, and why is a pyrolysis unit more similar to a power plant in this than to a fertilizer plant?
Yeah, good question. So it certainly would be possible to produce food-grade CO2 from that. I mean, at the moment, most of them are being regulated to, well, certainly I'm speaking more about the UK because I know the country better. They need to remove that CO2, but they're not necessarily allowed to utilize it. It needs to be then sequestered. So I guess technically it's feasible, but they don't seem to do it. I think they're being driven more politically by policy to sequester it. That was one part of your question. I'm trying to remember the second part, sorry.
Yeah, why is a pyrolysis unit kind of more, I mean, maybe you answered that. Maybe it's just the politics and kind of the regulations around pyrolysis units.
Yeah, I think that's it. So, clearly you've still got a pyrolysis, even if you're just utilizing that CO2, you've still got a pyrolysis plant which is capturing carbon in the biochar, and so you've still got the carbon credit side. You're still kind of positive or negative, and in that sense. So it's really just adding in that additional revenue stream. It's similar to the anaerobic digestion case where you're producing biomethane from a waste, but then you're able to get that additional revenue stream from the CO2 utilization. Is that all right? Great.
How many of these units do you have running?
Great question. This project, this is a demonstrator project that finished just at the start of this year. So part of the reason why we're here is because we're now on that commercialization phase. So we've got quite a few active discussions with people, nothing yet deployed, but a lot of conversations moving forwards into implementation phase. So, yeah.
Where is that demo project?
It's in the UK, near the south coast, or roughly between Brighton and London, if you know Brighton. But you're very welcome to come and visit, as is anyone in the room as well, if you're over that way. Great. If you have any more questions, we're also exhibiting, so we're at booth 305, so feel free to drop by. Okay, thanks.